Well, welcome everybody to the 55th edition of our SPCL Bcast. That's been quite a while. So I'm super happy to welcome Colin Raffel to give a wonderful talk about mixture of experts in MoErging things. So, and of course, as usual, Martin is going to give a formal introduction to Colin. Thank you.
Thank you. Thank you, Thorsten, and thank you, Colin, for joining us. Colin is Associate Professor at the University of Toronto, an Associate Researcher Director at the Vector Institute, and a Faculty Researcher at the Hagen base. His lab advances large-scale machine learning by developing decentralized collaborative model architectures, efficient training recipes, and risk mitigation strategies for state-of-the-art models. So without further ado, please, the stage is yours, Colin.
Great, let me just share my slides. Can you all see that?
Yes.
Okay, great. Yeah, thanks a lot for having me. I'm excited to talk to you about a line of work in my group that we've been executing on for a while now, and kind of share with you the trajectory of that research and some thoughts about where things are going. So to set the stage, I'd like you all to try to adopt this mental framework that I sometimes have, which is that a task, in other words, a set of queries and responses, can be considered as a composing required skills. So in other words, in order to answer some particular query, and here, of course, I have language queries because they're easy to look at and reason about, but you could imagine this for other domains too. You have some query, you have some input to your model, and you want your model to perform some processing and output the right answer. And I think it can be helpful and illustrative to think of these tasks as, or these queries as requiring a composition of skills. So for example, for the query, how long will it take for a penny to hit the ground from the top of the Empire State Building? Well, that requires some of what I would call world knowledge, which we can think of as a discrete skill. In other words, how heavy is the penny? How fast do objects fall? How tall is the Empire State Building? Once you know the answers to those questions, maybe you can perform some basic arithmetic. If you have another query like how does 12 cans of soda weighs, maybe the model needs to be able to do some grammar correction to parse the query, but it also requires world knowledge and arithmetic. And of course, there are many, many, many such skills. And you can think of kind of specific tasks that only use that skill. Like for arithmetic, what is 10 times 12 plus 3? There's really, you could argue there's really one main skill there apart from just language understanding in general. And I'm not going to claim that we can explicitly write down what all the skills are and which skills are required for a particular query. But when I talk about how models can generalize to new tasks or answer queries that are different from the queries that they were trained on, what I often mean is that the model itself has some collection of latent skills that we don't really know, but they are there. And we want the model to be able to compose those skills to answer the question correctly. And that's maybe one way of getting the kind of generalization that we like to get in models. So what is one paradigm for training models that has been shown to provide this kind of generalization? And again, this is not generalization in the sense of explicitly learning atomic skills and composing them, but just demonstrating capabilities that seem to provide evidence that there is a composition of skills involved that enables generalization to new tasks. And this paradigm is multitask training. And this has been particularly effective in language models. In fact, I would argue that most of what makes a language model useful comes down to this particular property of multitask training. But of course, this is, again, true in other domains as well. And to highlight my own work, which is not the only work to have demonstrated this, we showed in a paper a few years ago that if you take a language model and you train it on a bunch of different tasks, like a summarization task, sentiment analysis task, question answering task, and you express all of these tasks in natural language, in other words, a query that you or I could read and understand what we actually should do with the input, and you train the model in a multitask way on all of these different tasks, then you get this really nice generalization to unseen tasks. And again, we can't say in any precise way that it involves the composition of skills of the individual tasks, but we observe that kind of behavior. Now, I've kind of just used a lot of words to describe what we now call the process of instruction tuning of large language models. In this paper, we called it multitask prompted training, which I think is more descriptive, but sometimes more descriptive terms are more awkward to say, so we don't use them. But in instruction tuning of language models, this is exactly what we do. We train the model on a lot of query response pairs representing many different tasks, and then we find fortuitously that indeed the model does generalize to new tasks. So multitask training gives us this kind of generalization, and we call it zero-shot generalization because we say the model has not seen any examples of that particular task. And we can even maybe hypothesize or at least just imagine that this generalization involves compositional generalization of skills. Okay, so multitask learning is one way to do this, and it's very widespread. It's one of those things that people do all the time now. So I'm going to talk about an alternative paradigm for how we can get this kind of generalization. And really, I'm going to talk about two, but first I'll talk about model merging. And one way to think about what model merging is doing is that it's kind of a way of getting a multitask model without doing multitask training. But more broadly, the way that I like to think of model merging is that it just provides new paths for transferring capabilities across models that standard, sequential gradient-based training paradigms can't really do. So I'm going to use some really abstract diagrams to illustrate this point. So if we have a pre-trained model and we want it to be able to perform a new task, then one thing we can do to that model is fine-tune it. So we just take some examples from that downstream task that we want the pre-trained model to be able to perform, and we train the model on that task. And in this little abstract diagram that I'm drawing, the pre-trained model is the blue circle. We're training it on the yellow data set, and we get a yellow circle, which is a model that can perform the yellow data set's task. Okay. And there are other ways of giving models new capabilities or having them transfer capabilities across tasks and across training stages. One common paradigm called continual learning is one where we first train the model on task A, and then we train the model on task B. So we get a green model that works well on task A, and then we train it on the yellow data set, and we get a model that maybe does okay on task A because of this issue of catastrophic forgetting, where the model tends to forget the tasks that it was trained on in the past, in past training stages, as well as perform task B. So that you can see this is kind of a multitask model. Continual learning is one paradigm of getting a multitask model where we do training on each task sequentially, but it faces issues like this issue of catastrophic forgetting, which I'm not going to get into a lot of detail, but hopefully you can at least, if you're not familiar with the problem, you can at least imagine that the model sort of forgets what it learned in previous training stages. And then, of course, multitask learning, where instead of doing the sequential training, we actually just train the model on a concatenation of the yellow and green data sets, a mixture of those two data sets. And then hopefully, yes, we get a model that can do both things effectively. And so these are all kind of standard sequential gradient-based training paradigms for getting models to be able to do new things. And continual learning and multitask learning both provide ways of getting multitask models that have different trade-offs and benefits. But merging, which I would diagram something like this, provides a new way to transfer capabilities across models. It's a way that doesn't involve additional gradient-based training. And before talking concretely about how we might do model merging, which I'll talk about actually a bunch of different methods for doing model merging, I just want you to think conceptually about what model merging is actually doing. In model merging, we assume that we have different models that are very good, that might be specialized at some particular tasks. And we're going to perform merging, a procedure that I will define, that will combine those specialized models, a model that can perform the green task and a model that can perform the yellow task, into a multitask model, into a model that inherits the capabilities of the constituent models that are being merged. Okay, so we have, you can hopefully at the very least pictorially see how this is different from standard training. We only do training to get the individual models, we do merging to combine them without any explicit additional training. And one of the interesting things about this is that we can kind of combine these paradigms and maybe do some continual learning on the top and some standard fine tuning on the bottom, merge those models, and we get a model that kind of inherits all of those skills and maybe induces trade-off. So this is really, I see it as a new way, and by new, I mean new in the last, I don't know, 5 years or so, of transferring capabilities across models. So we don't have to perform training, and it's nice to not perform training because it's maybe computationally cheaper, but also maybe we could get around some of these issues that I mentioned, like the issue of catastrophic forgetting in continual learning. Okay, so now let me talk a bit about how we actually merge models. And when you work on a problem for long enough, and you see people reinvent the same techniques over and over again, and one day you sit down with Google Scholar and you try to figure out who really invented this technique. And right now, I think it was in this paper, which I think is from 1993. And this paper does an operation that we now would call merging. It does it for different reasons than the ones I just described. It does it more for like an ensembling style of motivation. In other words, we have lots of models that kind of do the same thing, but slightly differently, and we want to ensemble them to get a better model. But it does this very simple operation, which is actually how many people perform merging today, which is that if I have, in this case, 5 models, W1, 2, 3, 4, 5, which all share an architecture and an initialization, so they're all trained from this initial model W0, and I want to merge them, I just average their weights. I compute an average in parameter space of the parameter values, and I get W star. And that gives me my merged model. And again, in this paper, the motivation was that this merged model is better than any of the individual models because it performs kind of like a pseudo ensemble. But this operation is the same. And really, it's just that simple, right? And again, this is a common way of doing merging. It's common both in the kinds of workflows that I described where we want to enable, compositional generalization and blah, 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 blah. It's also common in practice in, let's say, federated learning, where this is people call this the federated averaging algorithm, where we just basically take a initialized set of parameters, train them on different or the same data set independently, average the resultant parameter space. So this is from a long time ago, and again, it's now been reinvented over and over and over again. In a paper from a few years back at NeurIPS, we wanted to think a little more deeply about what the goal of model merging could be considered to be. And so we wrote down this optimization problem that I've shown on the screen here. And it's a little bit opaque, but the basic idea is that we have capital M models that we're going to merge. We're going to assume that we have access to the model's posterior distribution over parameters, which is the distribution of values of theta, of parameterizations of the model, given the data set for that model, DI. And we're going to try to find a parameter value that maximizes a sum of log posteriors, which you can think of as like a product equivalent to being a product of the posteriors. And we also introduced this lambda sub I hyperparameter that kind of weights each individual model. In many cases, and if this is easier for you to think of it this way, you can just imagine that lambda sub I is 1 over M. Okay, so then it's kind of like each model has equal weight, but in some cases, maybe you want to upweight one model a little more than the other. So we throw in this lambda sub I term just to give people that option. Okay, so here is a optimization problem. Why is this reasonable for merging? Because we're basically saying we want to find a set of parameter values that is given a high likelihood, a high posterior probability for all of the data sets that we trained these individual models on. So this is a reasonable value of theta when we train the model on data set I for all I. Okay, that's what we're trying to do here. We're trying to find that balance. So I think this is a reasonable way to write it down of what our goal is. And in fact, if you assume that these posterior distributions are Gaussian and the mean are the parameter values of the model itself, and the covariance matrix is just the identity matrix, if you assume that that's how the posterior distributions are distributed, then you get parameter averaging exactly. Okay, and so again, this is a slightly more general version where we have lambda sub I instead of 1 over M. But if you do the substitution, then it works out how you expect. And I should have mentioned, why do we actually do this substitution? Why don't we just use the model's posteriors? Well, because usually we train these models with maximum likelihood-based training, where we only have a point estimate of this posterior. So we need to make some kind of approximation. And this is kind of like the most extreme approximation you could make, that, you know, the posterior distribution is just an isotropic Gaussian centered around the parameters learned by each individual model. Okay, so this is a very extreme approximation we can make. And what falls out? The standard way of performing merging, which is just averaging together model parameters. But let's see if we can do better. Maybe let's use the Laplace approximation. So if you're not familiar with the Laplace approximation, it uses this very special matrix called the Fisher information matrix, or just the Fisher for short. And it uses that as the precision matrix of this Gaussian distribution. And this turns out to be a good approximation of the model's posterior under certain assumptions and under, you know, I believe a first order Taylor expansion around a mode, around theta sub I, the mode that was found by maximum likelihood training. And we actually use an approximation to the Fisher, which is just the diagonal values of the Fisher, but and that's why there's a little hat over it, because the full Fisher is expensive to compute and invert. But in any case, this is a way of approximating this posterior distribution. It uses more information about kind of the relative importance of each parameter in estimating this posterior. And when we make this approximation, actually there is a closed form solution to the optimization problem still, which is shown at the bottom of the screen. And what's the difference here? Well, now we have these F hat I, these Fisher diagonal matrices in our weighted average. Excuse me, in our weighted average weighted by lambda sub I. But what are these diagonal Fishers doing? They're giving us a per parameter weighted average, where parameters in a given model that have a higher value on the diagonal of the Fisher are upweighted or downweighted if they have a smaller value. And the values along this along the diagonal of the Fisher actually are considered to be a reasonable notion of parameter sensitivity. In other words, how sensitive is the model's output to a change in this parameter? So you can kind of think of it like saying, if this particular parameter is especially important to the predictions made or the behavior of this particular model, then we're going to upweight it in the average. And if it's unimportant, we'll downweight it, okay? So that's what falls out of this analysis. And if we use Fisher merging, it kind of does what we want it to. And I don't have this result on the slide here, but it works a bit better than using the isotropic Gaussian approximation. But if we do kind of this esoteric merging pattern that I presented a few slides ago, where, you know, we take a pre-trained model like BERT, we do some continual learning on the top to first train on a data set called MNLI, and then another data set called RTE. And then we, in parallel, fine-tune BERT on a donor task, which are listed on the bottom of the bar chart on the right. And then we merge the donor task model and the RTE model to try to improve performance on RTE. How much of a boost do we get? Well, the original performance is the dashed line on the bar chart. And when we merge in the donor task model, we get these boosts in performance, which is kind of nice. And again, this is a way of getting a boost in performance without doing any additional training, and also where you are kind of recycling the donor model to boost performance on RTE. So this particular path of transferring capabilities across models would be either onerous or impossible with continual learning because of catastrophic forgetting, but it works quite well here. So merging, again, provides a new way of transferring capabilities, transferring skills, loosely speaking, across models. Okay, so hopefully you have a basic idea of what merging might be doing. You hopefully are convinced that Fisher merging maybe makes a better approximation to the goal of merging and works a bit better. And so then your question might be, well, why do we need to stop at using the diagonal Fisher for doing merging? Why can't we use, let's say, for example, a better approximation of the Fisher, like maybe a Fisher matrix that has non-zero entries in blocks along the diagonal, where the blocks correspond to parameter groups like weight matrices. We may call this blockwise Fisher merging. And pictorially, what we can imagine is kind of happening here in weight space is that the two original points are these circles, and the kind of valleys, this blue and yellow blob that represents the valleys, represents the parameters, the model's sensitivity to changes in different parameters in parameter space. You can kind of think of them as loss landscapes if you're familiar. So if we perform parameter averaging, we just draw a line in parameter space and we interpolate between these two models. If we do diagonal Fisher merging, then what we're kind of doing is we're measuring the direction of steepest change, or excuse me, we are choosing an axis, like the x-axis or the y-axis in this 2D picture, and we are moving along that axis in accordance to how steep the loss curve is on that axis. And then we're performing merging. And if we were to do something like a blockwise Fisher merging, well, then we're kind of choosing the steepest direction in this in the loss landscape and performing merging after we move in that direction. So in this made up cartoon on the screen, you can see why performing some kind of move in the steepest direction might be reasonable, because then if you interpolate between these two stars, you might end up in a region of parameter space that achieves low loss for both models. Okay. So then you might say, well, why don't we just do blockwise Fisher merging? Why don't we do something, a better approximation of the Fisher? Well, it turns out that there is no tractable closed form solution to blockwise Fisher merging. So in this paper that I'm mentioning at the bottom of the screen here, what we do instead is we kind of genericize many merging methods as solving the problem shown on the left there, finding a set of parameters theta that satisfies the equation on the right. This is actually a linear system of equations if you squint at it. And since it's a linear system of equations, we can find, if there's no closed form solution to the best value of theta, like there is for simple averaging, which is this isotropic Gaussian assumption, or diagonal Fisher merging, then we can use a standard method for solving a linear system of equations like the conjugate gradient method to find the best value of parameters theta star. Okay, and again, I'm not going to go into a lot of details here, but I want to highlight that the nice thing about this is that not only for simple averaging, this basic merging method where you just average the model's parameters, for diagonal Fisher merging, for blockwise Fisher merging, and in fact, for other merging methods that I'll mention on the next slide, you can cast them in this way. And this provides a way of, first of all, doing merging for objectives or frameworks that have no closed form solution like we had before, but also provides a different way of performing the merge, because sometimes, depending on how each of these methods work, there might be some numerical instabilities that make the closed form solution challenging to use in practice. Here, this provides a different way of performing merging. And so when using this framework, which we call merging by matching in task subspace, MATS, it allows us to flexibly swap different merging objectives and initializations and treat merging actually as a proper optimization problem where we perform optimization with conjugate gradient. So I'm not going to get into a ton of detail of this figure here, but the point that I'm trying to demonstrate by throwing this on the screen is that when we're using MATS, we can use different merging methods along the columns of these heat maps as initialization. So first we perform simple averaging, and then we can use MATS to actually perform the merge on top of that initialization using some particular objective, like the averaging objective, the diagonal Fisher merging objective, an objective based on a method called regmean, and so on. And you can see that not only do we sometimes get good performance when we do this, but what the heat map color is showing you is that if you perform merging, you can get a big boost over the value that you had at initialization. So in other words, if we do a simple merging method that has some closed form solution, but then perform MATS on top of it with a different, more sophisticated merging method, we can often get a big boost in performance. Okay. And sure enough, when we developed this method and published it about a year ago, it was state of the art for some of the standard settings where people test out merging methods. So here are just some performance results of using MATS on a NLP merging problem on top of the T5 model, and also a vision merging problem on top of the BIT-B model. Okay, and what's interesting here is that MATS outperforms these methods, even though it kind of, in some sense, generalizes many of them, right? And I think that ultimately is, first of all, because it enables using objectives that we can't actually find a closed form solution for, but also it may provide a more numerically stable way of finding this best set of parameter values. Okay. So one of the merging methods that I had listed on the screen there that I hadn't described yet, but I'll discuss a bit now, is a method called task vectors. In other words, doing task vector arithmetic. And task vectors are another kind of linear way of doing model merging. So you can think of parameter averaging as a way of linearly interpolating between two models. Task vectors are also a linear way of doing model merging. And you can actually relate it pretty closely to what simple averaging is doing, which I won't discuss now, but it's a fun exercise for you to do on your own if you're interested later on. But fundamentally, what a task vector is if you assume that every model that you're trying to merge is a fine-tuned variant of the same pre-trained model, then you can associate each fine-tuned model with a task vector, which is just the difference between the fine-tuned values and the pre-trained values. So again, when you perform fine-tuning, you're doing a bunch of gradient update steps, and finally you get your final fine-tuned model. And so the task vector just represents the change in parameter space that results from doing all of that training. So not a single step, but all of the training. And then this nice paper, which was not from my group, I should mention, showed that if you use these task vectors in certain clever ways, you can get models that either inherit the capabilities of the constituent models or maybe change the behavior, like trying to get it to, you can get a model to try to forget some behavior by negating the task vector and so on. But a very common way to use task vectors is for merging, which is shown here as learning via addition, where you simply take the task vectors, add them together, and then add their rescaled sum back to the pre-trained model, and that gives you a merging method. Okay. But when we're using task vectors in this way, one thing that this kind of ignores is the fact that when I update models, if I look at the per parameter change, basically each parameter in each task vector, fine-tuning on some particular data set may cause that parameter to change in some direction, and fine-tuning on another data set may cause it to change in another direction. And some of those changes are random, and the model might not be terribly sensitive to the exact magnitude of those changes. Okay, but what could happen is that if I take two models where for some particular parameter the change points in different directions, and I just average them together, which is what task vector addition of task vectors does, then the change just kind of zeroes out. And what that means is that the model doesn't get any change corresponding to either of the fine-tuned models. We're just basically using the pre-trained value, and maybe that's not such a good idea. And so we call this interference between the task vectors. And in this method that we call ties merging, which is trim, elect, sign, and merge, it aims to be a way to resolve this kind of interference. So what does it do? Well, first of all, it removes changes in the task vectors that are very small, because again, the process of fine-tuning model might introduce some noise, which basically results in trivial, unimportant changes to each parameter value. And those trivial, unimportant changes can stack and cause interference and problems when you add lots of them together. And then when the direction of change, the sign of the change for different task vectors that we're going to be combining disagrees, then we basically have them vote in accordance with the total magnitude in each direction, and then only retain those changes that agree with that. Okay, and then we perform a merge, and that gives us our merge task vector, which then gets again rescaled and added to the pre-trained model to perform merging. And what we find with ties is that, among other things, it does a little better in terms of retaining the individual model's performance, the constituent models being merged, when you are merging lots of models. So in other words, there's a less of a gap between the original performance of the models and the merged models on the tasks that they were trained on when you use ties merging, which is nice. So we kind of get a better multitask model when we use ties merging. But is that actually what we want? because remember at the beginning of the talk, I was talking a lot about how I want you to be thinking about compositional generalization. In other words, we have model A, which can perform some, encodes some particular skill, and model B, which encodes some other skill. And we want to tackle a problem that requires both of those skills. And the multitask framing of merging, if you ignore generalization to unseen tasks, doesn't really capture that. And so we got all riled up about this, and we wrote a paper about it, which we call Realistic Evaluation of Model Merging for Compositional Generalization. And a key part of this paper is designing an evaluation setting for merging that explicitly tests for compositional generalization. And so how do we do that? Well, we have a couple of different experimental settings. There's like a vision classification setting that's shown on the top, an NLP setting that's shown on the bottom. And the basic idea here is that we leverage some existing data sets to construct tasks that involve the composition of different skills. And in the vision setting, what do we mean by skills? Well, the ability to classify images from some particular domain we can consider a skill. So the ability to classify clip art images is a distinct skill, let's say, from the ability to classify real images. And similarly, the ability to classify between different fruits is a different skill to the ability to classify between different birds. Now, this nice data set domain net has many examples of images from different classes across many domains. So we actually can kind of construct this domain category pairing collection from domain net, automatically. And what we can do is then we can say that we are going to fine tune models on, for example, classifying drawings of fruit, classifying real pictures, and then separately classifying real pictures of birds, and then separately classifying clip art of tools. And then we can merge the models and test if the merge model can perform tasks that compose these skills that were unseen by the models being merged. Like, for example, can the model classify fruit that appear as clip art? And we can do the same thing for language. In language, we're actually, instead of domains, we're using languages. And instead of class categories, we're actually using different canonical NLP tasks like question answering or natural language inference. So in other words, if if one of my models can perform summarization in Thai, and another one of my models can perform question answering in Arabic, then can the merge model perform summarization in Arabic and question answering in Thai? Okay, and so that's what those little test tube emojis designate on the bottom there. And you notice that some of the entries of this table have no test tube emoji. That's just because there's no data set we could find that corresponds to that language and that task. So we can't test that, but we can get pretty close, okay? So now we can answer the question. If I take existing merging methods and I fine-tune models on these held-in skill combinations. So and by skill combination in the image case, I mean domain category. In the language case, I mean language task. So we fine-tune models on these combinations, merge those models, and then test it on unseen combinations of skills. How well does it do? It turns out not very well, okay? And in particular, here are three different settings we consider. We consider not only image classification, but also image generation. And you can see that just as you maybe inferred from the plot I showed from Thai's merging a few slides ago, in terms of the multitask performance of the model, in image classification and NLP, the merge models actually were quite worse in terms of the held-in multitask performance. In terms of the generalization performance, now interestingly, sometimes merging actually performed better than the multitask model. So that's kind of interesting. It means that merging could actually be a better way of getting compositional generalization. Interestingly, for image generation, we have cases where the merged models are better both in terms of the held-in multitask performance as well as the generalization performance. I should mention, just to interpret these plots, the star is the point you should be looking at for explicit multitask training. So that's where we just take the pre-trained model and we fine-tune it on all of the data sets corresponding to the tasks that or the skill combinations that the individual models were trained on. That's kind of the baseline we want to beat. All of the other shapes and colors are just different merging methods, and then these dashed lines correspond to the original performance of the individual models, okay? So merging isn't quite doing what we want, right? We want models, first of all, that match the multitask performance on the held-in data sets. And we also want models that generalize at least as well, if not better. And in fact, sometimes merging generalizes better. And actually in image generation, it generalizes better and gets a better held-in score, which is interesting. But in cross-lingual NLP, things look kind of like a mess. So it really depends on the setting. And that's part of where the first part of this title comes in, realistic evaluation. I think people should evaluate this in multiple settings. And another thing that we highlighted in this paper that's kind of orthogonal to the broader point that I've been making in this talk is just that different merging methods have different practical requirements that can make them more or less useful in different settings. Like, for example, the cost of performing the merge, or whether performing the merge requires access to the pre-trained model itself, or whether performing the merge requires access to data to fit hyperparameters or actually apply the merge. And this changes quite a lot across merging methods, and people are often not very explicit about this. So we're trying to force people to be more explicit. And in addition to having different requirements, what we find is that for methods that do have hyperparameters, they can often be very different in terms of their sensitivity to hyperparameters. So I won't go into a lot of details about this plot, but what we're kind of showing here is that if we index different possible hyperparameter values, the sensitivity in terms of the held-in accuracy of this case to these hyperparameter values can be quite different across merging methods. And as I mentioned before, the multitask performance tends to be pretty poor, especially as you scale the number of tasks. So in other words, the more tasks that the more models we're merging, the worse the multitask performance is of the merged model. One of the interesting things we find is that actually the more models we merge in, the better the generalization performance is. Okay, so this is, again, kind of shows you that merging kind of does what we want, but doesn't completely do what we want, and it changes depending on what setting we're in. Okay, so after we wrote this paper, we kind of took a step back and thought, okay, so if our goal is to recycle models, to enable compositional generalization, generalization to new settings, get multitask models by recycling models with no additional training, et cetera, is there another way to do that? And we've been working on just that, which we call MoErging, which is like merging, but with something that looks more like an MoE, a mixture of expert style model. And in particular, what we're going to be doing now in the talk is assuming that the individual models that we want to combine are built out of adapters. So for those of you who aren't familiar with something like LoRa, the idea here is that when I update my model, instead of updating all of the parameters of the model, I'm going to either insert or select a small number of parameters and only update those. And this turns out to work quite well. In the case of LoRa, what we do is for each or for some of the weight matrices in the model, we introduce a low rank update and we only train the parameters of that low rank update. So now we kind of have a pool of adapters, and in order to generalize to new settings, what we're going to do is each time we have a choice between a bunch of adapters at some particular layer in the model or for some particular weight matrix, we're going to feed the activations into a router, and the router is going to make a discrete choice, or as I'll discuss in a moment, a kind of soft choice or a soft weighting over the adapters in the pool. And so this looks like a mixture of expert style model. If you're not familiar with mixture of expert style models, then it doesn't matter. As long as you understand what's going on here, and that's fine. But you can kind of think of it as a way of turning a pool of adapters into something that looks like an MoE. So to kind of motivate that this actually makes sense as a way of combining, hopefully compositionally, the capabilities of the individual experts, I'm going to present some work on a method that we call soft merging of experts with adaptive routing, or SMER. And what SMER does, and this also makes a nice connection to all the merging stuff I just described, is rather than picking a single expert and routing the activation through that expert, what we're going to do is we're going to use the router to produce a distribution over experts and then compute an average of the expert's parameter values to produce a merged expert, and then send the activation through the merged expert. So the nice thing about this is that there's no discrete decision involved here anymore, right? training models that involve discrete decisions is generally challenging, and which is one of the main challenges of training MoE models, actually. But in this case, because we're making use of merging, we can do a kind of like soft differentiable routing, which might be easier to train. And sure enough, if we use smear instead of many baselines that involve one form or another of routing, typically discrete, you can see that smear ends up being Pareto optimal in this setting. And I should clarify, this is a setting where we're taking a pre-trained language model T5, we are fine-tuning it on 8 data sets, and we have 8 adapters, okay? And we're not explicitly saying, when you train on this data set, send examples to this adapter. We're just letting the model pick. And then at test time, we use the router to pick which experts to use or to pick how to weight the experts. So you can see that we get kind of like Pareto optimal accuracy. And in fact, we also get similar performance to routing the activation to all the experts and averaging their output, which is kind of an ensembling method. You can think of it as an upper bound that's quite a lot slower because you have to evaluate the output of each individual expert. One of the things we can look at to support this claim that smear or just MoE style models in general enable this kind of composition of capabilities is to look at the distribution of, or basically the average distribution over the experts for some particular data set. In other words, for examples in this data set, on average, which experts were given a higher or lower weight. And you can see that some data sets like QNLI basically all get routed to one particular expert. And interestingly, sometimes that expert is shared across data sets. So what does that mean? It might mean that those data sets have commonalities that would be beneficial to share parameters across. Other data sets kind of get routed across various experts, some of which are shared, some of which aren't. Like MNLI, you can see it's kind of split across 4 different experts. Maybe the model needs more capacity to fit MNLI, so it's using more capacity by routing to more experts for that data set. So you can see this kind of gives you the model a flexible way to learn how to share parameters or expand capacity to fit a multitask mixture of data sets. Okay, so that's kind of a way of training a mixture of experts model from scratch that has this kind of compositional generalization capability without explicitly specializing the experts. Now let's look at it from a different perspective, which is to say, what if we actually do have specialized experts, like I mentioned before? What if instead of just training the model multitask on all 8 of those data sets, we actually just separately train on each of those 8 data sets like we did for merging? But then after those experts have been trained, we have these individual specialized adapters, can we learn a routing strategy between those adapters post hoc? So not during training. We have a method for that. It's called post hoc adaptive tokenwise gating over an ocean of specialized experts, which stands for fat goose. And the way that we learn the router in fat goose is actually to slightly modify the way that the experts are trained. So we train the expert normally, and then after the expert is trained, this LoRa adapter in this case, we freeze the parameters of the expert of the LoRa adapter, and then we train we train a gate that decides whether to route each activation for each token in the input into the expert. We concatenate those routing vectors, that becomes our router, and as long as we make that little modification, which costs a little bit of more computation when we train the experts, we can then build a router and learn to do post hoc gating automatically. So when we compare fat goose to other methods for learning to route among specialized experts, it does a bit better. And in fact, we even have a setting in the paper where it performs about as well as if you just chose the expert that was the best for each particular task. And I should mention, in this experimental setting, we are explicitly looking at generalization. So we're measuring performance on tasks that we do not have an expert for. So we can cheat by sending each expert to each example to the expert that's best for that example. And fat goose gets almost as good performance as that. One of the interesting things we can do after we build a model out of fat goose is we can look at which expert was chosen over the course of processing some particular example. And so that's what we're showing here. Along the x-axis of this heat map are the routing distributions of different of different layers in the model. First, the encoder layers and then the decoder layers, because this is a T5-based encoder-decoder model. And then along the y-axis is the different choice of module or expert or LoRa adapter, all kind of mean the same thing. And so you can see that which expert gets chosen is actually quite different for each router, right? So each of these columns corresponds to a different router in the model, a different pool of adapters that can be chosen from. You can see there are some experts that get chosen more often than others, but what's most interesting about this, I think, is that if you look at the oracle, in other words, the expert that would be chosen for this downstream task if you could cheat, it actually almost never picks the oracle expert, but it still gets better performance on this particular held out dataset CB. So in a way, it's kind of learned a routing strategy that composes capabilities across the experts that outperforms what would happen if you had to pick a single expert. And this behavior kind of emerges in a nice way. And I should say that our work on Fat Goose is not the only work on MoErging. We've kind of gone back and looked at a bunch of past papers and pointed to them and saying, that's MoErging, that's MoErging, that's MoErging. And we wrote a survey on this where we try to kind of characterize methods in terms of design choices they make. In other words, does the training of the expert models have to be done differently? You know, do the people who train the experts have to share their data? How are the experts' outputs aggregated, and so on and so forth? So if you are interested in this general direction, at the time of publication, I don't know, 6 months or so ago, this aims to be a pretty comprehensive collection of all of the papers that you might squint at and consider to be MoErging. So I'll end there. I will say at the end of all of my talks, I always say that if you want to give me feedback of any kind, like if I talk too slow or too fast or cover too little or too much, or my slides should be changed in some way, you can give me anonymous feedback at the link there. But if you want to give me non-anonymous feedback or ask me a question, you can just email me. My email's on the screen there. So I'm happy to take questions now if anyone has any.
Thank you, Colin. I will take a quick second to advertise the VCast in 2 weeks on the 13th of March. We will have John Mellor-Crummy, and the topic will be measurement and analysis of application performance on GPU accelerated systems at exascale. Now I think we can go to the questions. Patrick, I think you can unmute yourself.
Yeah, so thank you for the talk. I've got one question. I'm not sure if I got it right. So basically, when you're performing merging and you tried it on domain generalization task, like when you perform merging, do you actually use some of the knowledge from where does the model, from which domain does it come from? Because I know like in domain generalization, some algorithms use like the difference in means and covariances of the domains of feature distributions.
Yeah, so for the methods that I described in that study, those don't use that information. You know, you can think of parameter averaging, which it of course doesn't. It just averages everything together, and all of the methods operate kind of in the same way. They're kind of agnostic to what specifically. Arguably, you could say they're agnostic to what data or what domain the model was trained on. There are MoErging style methods that do make use of that kind of information, like statistics about the data that a given expert was trained on might be used to determine how to route. And if you look at our taxonomy, trying to think of the right way to look at, so those are cases where we would say that the expert training data is shared, and the routing data set is the expert data set. So if you want to poke through and find some of these methods. So yeah, so for merging, I would say no, but for MoErging, in some cases, yes.
And I've got a follow-up question. So in all of these settings, what is your assumption on the architectures of the models? Like, are they more or less uniform? Do you use like kind of small GPT-2, larger GPT-2, or can it be like an MLP and a GPT-2? Have you like seen a difference in performance if you have a larger variance?
You mean merging models that have a totally different architecture? Yeah. So almost. So it's a very interesting question. Almost all merging methods not only assume that the models being merged have exactly the same architecture, because then there's kind of a one-to-one correspondence between the parameters, but it also assumes that they're fine-tuned variants of the same pre-trained model, which among other things tends to mean that you don't have to account for certain symmetries, like the permutation symmetry of activations in neural networks. To merge capabilities across models that don't have this one-to-one correspondence is kind of an open problem, and it's non-obvious. A very simple way that you could imagine doing that is via distillation of some kind. But to do something that doesn't involve distillation or subsequent training, I think it's an open area of work that we're working on in my group, I should say. Yeah, but yeah, I don't know of any methods that can go quite that far in terms of differences in underlying models. It looks like Thurston was asking for Fisher-based merging. Do you analyze how much a better approximation of the Fisher matrix helped the overall result? A bit, yeah. So the two ways that we did that, the first was in the actual Fisher merging paper, we have an ablation measuring the impact of performance of estimating the Fisher on a different number of examples, because I didn't throw this in the slides, but when you compute the Fisher, the way you do it is by computing the average of the squared gradient over some subsample of your data set. And so the more examples you include in this average, the better of an estimate this is. And what ends up happening is that above a certain threshold, which is a usually pretty small number of examples, like a few hundred examples, there's no real improvement in performance. The other way that we analyzed this was in the follow-up work on MATS. We considered a merging objective that effectively uses a blockwise Fisher merging objective, and that turns out to work a bit better, as you might expect. Yeah. So.
Yeah, thanks. I have actually a follow-up question. So you mentioned distillation. Did you compare to distillation as a merging method, or does this even make sense?
Yeah, it does. I think it does make sense. It's almost never included as a baseline, just by virtue of the fact that these merging methods tend to be dramatically cheaper than performing any significant amount of training, right? I mean, if you think of parameter averaging in particular, parameter averaging is like about as cheap as like a single forward pass, right? And some of these other methods like MATS, which uses conjugate gradient to find these parameter values, the computational costs do increase, which is what I was trying to highlight in that table I threw on the screen. But in terms of actually just comparing directly, I think people usually don't do it. I will say that for companies that are deploying techniques like merging, and they want to transfer capabilities across models and get multitask models and recycle things and so on and so forth, I know they do actually use distillation sometimes, because when you're at a company, you just want to make the numbers go up. You don't actually care if things are really expensive. And actually, in the stuff that we're starting on along the lines of cross-architecture merging, which I was describing a bit ago, in that case, I think distillation can and should and will be a first-class baseline.
Okay, thank you. Great talk, by the way.
Thank you.
I learned a lot.
I think we don't have any other questions.
I've got one more question. So, since you drew the analogy with federated learning, and in federated learning, there is always research going on with the malicious clients. Is there also a setting where you kind of consider malicious experts while merging that?
Yeah, so I will say that the relationship between the work that I've described and the work that I do in my lab and federated learning is always a little hard to draw, because some people, when they say federated learning, they really mean like we're going to be doing distributed, privacy-preserving learning with very little communication overhead. And sometimes when they say federated learning, they really just mean we're going to be doing distributed training with little communication overhead, and they don't actually care about the privacy stuff. And when you make the communication overhead really, really, really low, then yeah, it pretty much just looks like model merging. And in fact, you can, as I sort of said earlier, you can think of federated averaging as a merging method. And in fact, we use emerging methods just like that. But the research that we've done in my group generally assumes, first of all, that people are not worried about the privacy of their data, that we're, so we don't have to design around that consideration. And second of all, they're not worried about the privacy of their models, the models themselves, because they're sharing these models. So all that is to say that we haven't thought about like malicious models in the merged pool of models explicitly, but you could imagine that methods that kind of do a form of adaptive merging would automatically kind of remove those. And some of these merging methods, again, we kind of had to really squint at different methods to decide if they could be considered what we were calling merging. Some of them do something like that, like, and in particular, if you just imagine that in order to maximize performance on some particular task, we're going to upweight or downweight different expert models in a merge. You could imagine kind of implicitly downweighting models that end up harming performance. Now, in terms of backdoors and malicious behavior that's harder to detect or might not be picked up by just measuring the loss on typical examples, no, I don't think any of this stuff has touched that.
Okay, thank you for the talk and the answers.
Sure, yeah. Yeah, and I should say, if anyone has follow-up stuff, I'm always happy to talk about this. So feel free to shoot me an email or give me feedback.
Thank you. Thank you very much.
Thank you.
Yeah, thanks a lot for having me.